welcome to the power system protection course. So, we are in the relay lab to verify the different relay characteristics. In this experiment, we will verify the differential relay characteristics specifically on percentage biased differential relay. So, we have studied in the theory that the transformer, 3-phase transformer specifically is being protected by differential relay, and the characteristic which is being used is percentage biased characteristics. In the percentage biased characteristics, we talk about operating current versus the restraining current, and there we will try to see that whether the corresponding relay is operating in the trip region or not. For that we have a experimental setup which I like to show you here also in our demonstration, and that before that we will go for the corresponding circuit connection, the theory and the settings in the relay as usual, and finally, we will have several observations to test the characteristics for different settings which will be accomplished through this PC connected to the relay. Now, as to clarify on our the operating current and the restraining current perspective, as we have already discussed in our lectures, that if this is the transformer, then we have a CT group in the one side and CT group 2 side. So, we can consider this side as a low high voltage side and this side as a low voltage side. Then the differential branch, the corresponding differential relay happens to be in this branch, and the operating current for the internal fault, it becomes the corresponding secondary current in the high voltage side plus the secondary current in the low voltage side. So, this is the corresponding CT connections that we have carried out here in this arrangement, and based on the internal fault case, we will say that for this the corresponding relay should go for a trip decision. So, we are using here Micom P634 of Schneider make. This is our 87T, those so called as per the IEEE number. So, purpose is to verify the percentage biased differential relay characteristics, this characteristic which you already know. So, here we talk about the operating current y axis and the restraining current on the x axis. So, here this is about no trip region, assuming this is a normal operation situation, and this is about the trip region. We are in this verification, we are considering two slopes, a smaller slope in the low region of the restraining current and a higher slope in the higher value of the restraining current, because in case of the external fault or through fault case beyond the transformer, the current if it is higher current, the CT saturation may lead to maloperation of the particular differential relay. So, therefore, the slope of M2 is in general higher, that we know. And before that we have a minimum, we can say that threshold setting, that is I pickup current setting, upon which you can say that the relay takes the decision. So, above this curve we have a trip decision, and below this curve we have a restraining decision. So, what we like to verify here is that when for a given value of restraining current, note for a given value of restraining current, how much operating current is required for the operation, that point is nothing but the corresponding characteristics point. So, given the setting of M1, M2 and IPU in the relay, we like to verify that whether the corresponding characteristics is being obtained for the particular setting, particular arrangement for the transformer or not. So, what we will do that we will set a restraining current by setting the load current in the arrangement, and then we will increase the differential current and see that at what point you can say that the corresponding the trip happens to be there. So, that point of observation will say that yes, that is the point of observation of our particular relay characteristics. For that we see here that already we have discussed in our lecture. Let us say this is high voltage winding one side and 2 is a low voltage winding, any connection as you know, star, delta, delta star, whatever it may be. The CTs are connected in star grounded both side CTs in the numerical relaying connections, and so we know it. And then we have the normalizations at both the sides. We have zero sequence eliminations both the sides to because in we know delta side line current does not have zero sequence, but star grounded side line has zero sequence. So, zero sequence there is extra current that happens to be there in the star grounded side, that has to be subtracted. And then we have the vector adaptation for the different connection of the transformer YD1, YD11 and so. For that the vector adaptation is being carried out at the low voltage side as already discussed in the lecture, and we have a matrix for that to multiply the different 3 phase currents to get the required current. And after the vector group adaptation, the differential current is being computed for the particular relay characteristic. This differential current is this operating current perspective, and in this portion the relay takes the decision using these percentage bias characteristics. And we see here in the normalization part the corresponding rated current of the high voltage side and rated current of the low voltage side are being used for the normalization perspective and so. Now, the in this case this is that MICOM relay P634 that part. So, this takes currents inputs from the high voltage side and low voltage side to here, and this is our transformer here. We have taken a 220 volt 110 volt transformer for this our case, and each transformer is having a single phase the corresponding single phase bank up transformer, and each one is having a 3 kVA rating to, and that we are using for this, and the corresponding supply is 220 volt 3 phase supply, and this 110 volt side is the load side, and we have a 3 phase load bank of loads, 3 blocks of loads are connected for this arrangement. Now, what we do here is that we vary the corresponding load that results in the corresponding restraining current to be more and more, because the corresponding load current in the secondary side corresponding primary current also increases. So, we set a particular loading condition. So, that gives us the corresponding restraining current, that is this I 1 plus I 2 divided by the 2.5, we will talk about that. And then on this perspective you can say that the we go on here for the differential current, we have created a path for the internal fault in the low voltage side here in between the two side CTs. This path is for the internal fault creation in one of the phases, and we have a resistance here, and this by varying the resistance we can vary the corresponding current to this one. So, what we do that from a high resistance we go on decreasing the resistance till the corresponding current becomes more and more, and at a particular setting for this restraining current at a particular value of this resistance, the operating current becomes sufficient to trip the relay. Once the relay trips, this circuit breakers supplying feeding the power to this transformer gets opened, and that is what the functionality of this case. However, this particular relay is used for the high voltage systems, and therefore, we have tried to emulate the corresponding things based on the 220 kV to 110 kV systems. That is what accordingly corresponding the CT ratio and the PT ratios are being considered in the relay setting perspective. Now, in the relay settings we have the corresponding transformer, this 220 kV is to 110 volt and 110 kV is to 110 volt. These are the PT ratio. We have the CT ratio of 2000:5, 1700:5 and so, and for the percentage bias characteristics we see here in the characteristics we have considered 3 sections: section 1 this portion, section 2 this portion, and section 3 this portion. For M1 the lower slope ends, you can say that that between for the section 2 and section 3 you can say that is for the M2 section. So, in the settings we need to fix up this IPU, we need to fix up this M1 and the M2, and also the corresponding junction points, the crossing points I restrain M2 and the corresponding I restrain M1 and so. So, that is about that, and the reference current as it is called is based on the consider the MVA rating of the transformer upon the root 3 V nominal high voltage side voltage, rated voltage, and the low voltage side reference current is taken from the the MVA rating of the transformer and the root 3 the corresponding V nominal voltage of the low voltage side. For each phase the I operating is based on the corresponding I high voltage plus I low voltage, these are all again normalized current. So, that is why they are per unit current, and sum of these two you can say gives you the I operating, and I restraining is the subtraction of these two side currents after the normalizations and multiplied by 0.5. So, this is what the corresponding I operating and I restraining are calculated, and as already mentioned that we go on varying this I restraining and see at a particular point what the corresponding differential current, minimum differential current required to trip the relay, that gives us a point. So, we draw the particular characteristics curve as per the setting, and that is our reference, and then we go on increasing the differential current for a given restraining current to find that particular point and we note that point and try to see that yes, are you getting this corresponding characteristic curve as per the setting or not, that we like to verify. We will see the different components on the table, which is arranged for the demonstration of this experiment, verification of the differential characteristics. So, we will start from the supply. So, this one we give this provide this 3 phase supply to 20 volt 3 phase, and then we have the bank of transformers. So, these are each are you can say that 220 by 110 volt single phase transformer having 3 kVA each rating. This primary of this transformer is 220 volt side is being supplied from the source, and the secondary the low voltage side 110 volt side is loaded, and we have bank of loads. We have bulb loads for the minimum load, and we have the bank of gang rheostats to load it further, which help us in varying the corresponding I restraining part. Now, this is about the supply and load and in between the transformer. Then to the connection to this relay, the relay here is MICOM P634 relay. To this relay we now need the connection of the primary side CTs and secondary CTs. The corresponding primary side CTs are here and the secondary side CTs are here. So, primary I means 220 volt side, high voltage side, and these are the low voltage side CTs connected to that. And we have a PT also connected to the high voltage side, and the low voltage side is directly connected to the relay. In addition to that, we have to the neutral, because the connection of the transformer for this case is both sides are star grounded. Why I have considered star grounded? It is easy to understand for us, clarity. Otherwise, someone can take any connections based on the requirement and so. So, both sides are star grounded. So, we have 2 CTs on the neutral side also, which are being connected to the particular relay for applications. Next, to create fault, as already mentioned, we have a resistance path in one of the phases connected to the ground. So, that by varying the resistance we can control the internal fault at the low voltage side of the transformer, as already mentioned, and that is what the corresponding these two rheostats are there to control the current in the internal fault path. So, the fault path current is being controlled by this resistance, and from higher resistance to lower resistance we can go on increasing the current, and whenever the corresponding for a given setting of the load and the characteristic happens to be there for the particular relay, we go on increasing the differential current, and at a particular point the relay trips, that point we notice and observe, and that gives us the corresponding point in the relay characteristics. Once we have that trip, then the corresponding circuit breaker here trips, and it trips the corresponding supply, protecting the corresponding transformer. In overall we saw this, the corresponding relay here is being there, and this relay is connected to this PC to have the corresponding all details as we have already seen in earlier experiments also. And this clamping meter provides us the corresponding current in the fault path, and the load current is being observed from that the corresponding the clamp meter that clamp meter. So, we have two ampere reading on the fall path for the fall path current and also for the restraining current perspective, we have that the other you can say that clamp meter is being used. So, this is in overall about this arrangement in this case. So, what we will do in the during the demonstration perspective, we will go on changing the load by varying these load rheostats and the corresponding fixed valve load. That part gives us the load part, and the fall resistance here by varying this one we control the corresponding differential current path. So, we will see the settings which is being carried out for a particular case in the relay. As already mentioned, we are verifying the percentage bias differential relay, where we have different settings like M1, M2, IPU and so. So, we like to see that what are the settings we have carried out for this case. So, this is our the corresponding primary and secondary voltage rating 220 kV, 110 kV and so, and we have the corresponding settings for this relay. M1 the first slope happens to be 0.5 for this case, and M2 happens to be 0.9 a higher slope 0.9 here in this case, and then we have the corresponding the transition from this the second section to the third sections that happens to be at 1.5 I reference in per unit. So, these are the corresponding settings. In addition to that, we have several settings as known, you can say that for the percentage bias relay, we have the corresponding overflow setting and the corresponding percentage of fifth harmonic and so, and then we have second harmonic, you can say that inverse setting of 29% here, and the fifth harmonic is setting of 20% here for this case perspective. So, this shows us the overall setting which is being carried out for a particular case, which like to verify and demonstrate on this experiment. So, we will demonstrate now. Already this power supply is given to this, and you see this bulb glowing. So, those are the loads connected to the secondary, the low voltage side 110 volt side. So, that is the minimum load we are maintaining for this arrangement. In addition to that, as already mentioned, we have the corresponding other loads also will be connected to increase the load capacity. So, if you see here the corresponding currents are available here in this case, the it is clearly showing about that on the primary side and the secondary side. Now, we can increase the load here and see, we can increase the load here, and then we will see the corresponding increment of load here also. If you see here, the corresponding load also increases substantially. So, like that we can go for the further load increment, which gives us the corresponding values of particular restraining current we require for the observations and the verification of the relay characteristics. So, then we will talk about the corresponding how the corresponding relay operates for a given things. For that the as already mentioned here, on the differential current perspective, the fault current, the internal fault current has to be increased. So, for that we will go on increasing the corresponding current by decreasing the fault resistance which is being connected to one of the phases. And for that we will see the corresponding current here in this one, and the load current can be seen from here. So, we see here the corresponding load current is now 0.2 ampere for this minimum load basis for this bulb. So, we will see now how the differential current can be changed. So, this is the switch for the differential path, and the resistances are connected for that particular phase, the internal fault creating. So, if you see here, the current now showing is 0.5 ampere in this faulted path current. We will go on increasing the corresponding current, and we will see here now this corresponding current will increase in this path. So, it is 0.6, it is 0.7 and so. So, you see here that by controlling the resistance we are able to increase the fault current path currents. We will see in the relay what is the corresponding restraining current and the differential current. So, you see here the corresponding reference current is 0.073. So, this is differential current and this is restraining current. So, then by varying the differential restraining current and the corresponding differential current will be changed till the corresponding trip happens to be there. So, one point here you see here, because we are varying the corresponding differential current by the arrangement of these rheostats. So, this is not that perfect smooth point we will get, because there will be a lot of variation here. In addition to that, the corresponding voltage also from the supply side there will be little bit variation. So, in the characteristics which will be getting, you may not get the exact things, but by and large you can say that these variations will be must be taken into account while discussing the verification part, and so this is the limitation of this experimental setup. Now, by further for this particular loading condition, minimum loading condition as we have already mentioned, we will go on increasing the differential current, and then we will see that when the corresponding relay is tripping. So, that point you can say that we will go on noticing the corresponding current from this relay there, and we will see, you can say that at what point the corresponding trip happens to be there. So, that observations we have to do, and we will see what will happen to this perspective. Yes, you see here now the bulb glows. So, this trip happens to be there. So, that is what the corresponding red signal of the trip of the breaker also, trip of the relay also happens to be there. So, that gives us that yes, at a particular point of the differential relay characteristics, the corresponding the corresponding relay takes the decision and trips the particular breaker here. And like this we will go on noticing at different loading conditions on increasing the loading condition on the using the corresponding loads, and for that one we go on varying the differential current, which will be more and more as per the characteristic curves, and you noted that good all these points for the particular setting, and that we have the reference curve from the perspective, and then we the corresponding observations points were noted, and then we proceed for the verification part. So, now we will see for the particular setting, this is test case 1. For the test case 1, we have m 1 equals to 0.5, m 2 equals to 0.9 and I p equals to 0.2 already shown in our relay setting part. So, for that we have the different measurements and observations. We have measurements on the transformer side through this particular two differential relay branch and the restraining that load side current. So, this is about the load current, and these are the corresponding fault current. So, as already mentioned, we vary the load currents, and you notice the corresponding fault current, minimum fault current at which the corresponding relay trips. Like this we go from the 0.2 ampere to the 0.2 ampere to the as high as 12.8 ampere on the loading perspective vary, and the corresponding fault current goes on increasing as you know from the percentage bias characteristic perspective. So, this part is observed from the relay data as already mentioned in the taken from the relay directly measured from taken from the relay you can say the perspective. These are the per unit data available for that one, because our plottings are based on the per unit also. So, we see here that the for this corresponding 0.2 load current and the corresponding fault current, the corresponding restraining current happens to be 0.026 per unit as per the after the normalization and so, and the differential current at which the corresponding relay operates is 0.173 per unit, and similarly for the any other observations if you see here for the 2.4 load current, the load current increases now. So, it means the restraining current also increases, and then the corresponding fault current happens to be there 1.568. So, that the corresponding that is also higher. So, the differential current also higher. So, like this we go on observing the for the different load currents, increasing load currents, the restraining current also increases, and the corresponding differential current at which minimum differential current at which the corresponding relay trips are being noted down. So, then we plotted this corresponding the different restraining current and the corresponding operating current. The brown line is the corresponding curve which is there for the particular setting percentage bias setting considered for this m 1 equals to 0.5, m 2 equals to 0.9 and I p equals to 0.2, and we have the 3 sections, section 1, section 2 and section 3 as already mentioned. And then we the points which are marked here are the observation point taken from this the corresponding differential current for the particular restraining current in per unit. So, these points are there and plotted. Now, we see here in this region it is almost matching, and in this region there is little deviation. As already mentioned, the difference from the said value, which is being the reference, you can say that for this one, which is expected to the relay should able to perform for the particular experiment. What you observe in this experiment, that there is little bit deviation in this perspective and so, and this is due to the because we are varying the minimum current to the fault current path in the resistance. So, the resistance smoothness of that decides the corresponding current. So, therefore, the minimum current going on increasing leads to little bit of error here for that perspective. Otherwise, it is clearly observed that the corresponding relay performs as expected, as set for the particular case. We have now will see how the corresponding relay calculates the operating current and restraining current for the differential relay operation. For this, first, as already mentioned, we will calculate the reference current, and the reference current happens to be the kVA rating or the MVA rating of the transformer upon the root 3 V high voltage side or the low voltage side. For this case, in the high voltage side, reference current happens to be 125 ampere, and the low voltage reference current happens to be 250 ampere in the calculation process. So, at a given instant of time, the corresponding high voltage side phase A current happens to be for this internal fault situation happens to be 60 ampere, and the low voltage side phase A current at that time happens to be also 60 ampere. Now, this happens to be in phase A, in the phase A perspective for both the sides. So, we have created the fault also in phase A. In that sense, the operating current is being calculated for this 60 ampere upon the corresponding rated current in the high voltage side minus the corresponding 60 ampere upon the rated current of the high voltage side. So, this gives us 0.24 pu of the operating current, and if you see this corresponding screenshot available, then it is clearly showing that the I reference from this relay happens to be 0.239 pu. So, this 0.239 as compared to 0.24. So, therefore, this is in agreement with the relay calculation process. Similarly, for the restraining current, it is calculated in terms of this 0.5 with 60 upon 125 plus 60 upon 250 for high voltage and the low voltage side correspondingly, and this gives us 0.36 per unit restraining current. And if you see this from the screenshot, this the corresponding relay provides the measurements of 359 pu. So, which is also in agreement to this what actually the relay is calculating. Thus, through this we are able to know that the restraining current and the corresponding operating currents are how being calculated or processed by the corresponding relay. We have another test case for the M1 equals to 0.5 and M2 equals to 0.9 and IP equals to 0.2 in this case, and then we talk about the vary the corresponding load current here in this set case M2 equals to M1 equals to 0.5, M2 equals to 0.7 here, and then IP equals to 0.2, and then we vary the corresponding load current here, and so also the fault current here path, and we observe that the restraining current is also increasing in accordance with that, and the corresponding minimum differential current to get the corresponding characteristics also goes on increasing. We plotted them again like the earlier case, and we find that the corresponding points are in agreement with the relay characteristic which is being set for the particular case. So, in overall we see that the relay characteristics which is being set for the particular case is in agreement with the particular setup for the transformer, 3-phase transformer protection differential relay percentage biased characteristics. So, what we see that the differential relay for the transformer protection is very powerful, but as we know in case of light load or no load condition, when the transformer is being switched on, inrush current flows depending upon the different factors like the residual flux, So, and the CT the corresponding connections of the transformer, voltage switching on instant and so. So, that current flows in the one of the sides, thereby the differential current becomes significant, and in the percentage by differential characteristics it lies in the trip region. This is not being a fault situation, will unnecessarily trip the relay, that is not desirable. At that time the corresponding relay should be blocked not to operate the breaker, so that there will be no power interruption from the grid operation perspective. Here is the corresponding inrush current collected from this experiment. So, we see here that the inrush current contains lot of harmonics. This is, if you see here, the corresponding current happens to be a wave shape which is no more sinusoidal, and if we analyze this one to the FFT analysis, it clearly reveals that the second harmonic and fourth harmonic component are much higher in this case with respect to the fundamental for this waveform, experimental waveform it happens to be 75%, fourth harmonic 20% and fifth harmonic 18% of the fundamental and so. So, this reveals that if this amount of current which happens to be maybe more than 5 times of the corresponding current in one of the phases, then it will operate the differential relay. Therefore, in this relay experiment the corresponding settings to restrain the relay to block the relay operations is be accomplished. In particular experiment we have second harmonic restraint which happens to be a particular setting, and that is is decided by the operator as per the requirement. Another situation which comes in the differential relay issue is about the overfluxing, as already enumerated in the lectures. So, whenever the voltage happens to be higher, the corresponding inflow of current similar to the situations of the inrush, the inflow of current becomes enormously high, and thereby the if you see here it may also lead to operation of the differential current, it will fall in the tip region and lead to again unnecessary tripping. To avoid that, if you see this corresponding waveform collected through the oscilloscope like the inrush current for the transformer, we see that there is a lot of harmonics content here different from the earlier case, and if you see here predominantly there is a fifth harmonic significant component here, and this fifth harmonic is being with respect to the fundamental. This is for the fundamental, third harmonic and fifth harmonic. So, with respect to the fundamental, the fifth harmonic percentage is being quantified, and that blocks the corresponding relay operations in general. So, therefore, in the relay, in this particular numerical relay, we have to block this such situations not to operate the relay, we have the fifth harmonic blocking. As already discussed in this slide, the inrush current creates problem to the differential relay, because during the inrush situation one of the side is having large amount of current, and the differential current falls in the trip region of this characteristics. So, we will now demonstrate how the differential current creates issue and the corresponding solution strategy. For that, as already mentioned, we have kept the corresponding the operating mode inrush to be without. So, there is no inrush blocking arrangement as of now in this setting, and the relay is set in accordance with that. For these situations, we will see that no load is connected, no internal fault, and we will switch on the supply rated voltage to the 3-phase transformer, and the 3-phase transformer will be energized, and we expect that at least in one of the phases the inrush current will be significant, and the relay is expected to operate because no restraining is there in the setting. Let us see this demonstration. I am switching on the supply to the transformer. So, we saw that the relay operates and the bulb glows and the supply is being cut up to the transformer. So, this clearly demonstrates that with no restraint setting for inrush current situations, the differential relay operates, which implies that the theory behind this is okay. So, to overcome this problem, because this is not a fault situation, the corresponding restraint current for the second harmonic restraint as available in this particular relay has to be set, and typically we can have this setting more than 70% or 17% or so, depending upon our convenience and so. Now, we will demonstrate that with the second harmonic restraint setting. So, for here for example, we have set the inrush setting to be now active, and then it is on 29% setting, and we will see that in these situations when you switch on, like the earlier case we saw about this inrush was leading to operation of the relay. Now, we will see that the inrush with these restraint features included in the setting, whether the relay will operate or not. As expected, the relay should not operate. So, I am switching on the supply without any load or without any fault, and then we will check whether the relay is operating or not. So, the supply is switched on to the transformer, but the relay is not operating, no bulb glows, no circuit breaker operations. So, the supply is being maintained. So, this clearly shows that with such a second harmonic restraint features in the transformer, the restraint of the corresponding inrush current situation is being blocked from the any operation of by the relay. Now, we will test the other case for this situation, that now the overproxying operation is active. So, it is yes mode for the relay setting, and the fifth harmonic with respect to the fundamental is being 20% for this case already set. So, we expect that the corresponding relay should not operate for over voltage situation or so. So, I will demonstrate by increasing the voltage, we will see that the corresponding relay should not operate. So, I am going on increasing the voltage substantially, and then we see that the relay does not operate. So, with this high voltage also the relay is not operating, and it clearly shows that the corresponding restraining feature is successful in blocking the relay from operations, even though the differential current happens to be significant during this no fault situation. So, overall the remarks is that we verified here for the star grounded transformer, one can do the corresponding connections different and can test the corresponding transformer. It is no problem, because the corresponding differential relay percentage by differential relay takes care about the vector group adaptation. So, accordingly the vector group adaptation number should be put there, it eliminates the 0 sequence. So, absolutely no problem. So, we can one can verify for other connections in the particular setting in these experiments. Thank you.